Hello everyone, welcome to college algebra last section. So we're not doing like the next two sections that we normally do. So in a way, we should all be pumped that we can learn this material since it's not that many sections. So let's all try to get a good grade in this course. Okay, let's do section 4.6, which is logarithms. Okie dokie. Let's start off with these basic ones here. What's log base 5 of 125? Well, logs are the power. You raise the base to get the argument. 5 to the what power gives you 125? 5 to the third power. So the answer is 3. Let me write that down. Let's see. Equals 3. Since 5 cubed is 125, I can write that down too. Here's the equivalent exponential form. The base of my exponential form is going to be 5. 5, just like the 5 there, the base for the log. Logs are equal to the exponent. That's where the exponent goes in exponential form. And it equals whatever's left, the argument. And sure enough, that is a true statement, which supports the idea that 3 indeed is the correct answer. What about this one? When you look at this problem, we want to evaluate this. You got to think of that idea. And again, you got to go through the Rolodex of all those log properties. And the one screaming out here is, I see a log whose argument is an exponential. So that's your tip-off. Oh, that's composing inverse functions. So the initial input, which is the exponent, equals the final output. Assuming these bases are the same. The bases have to be the same in your log and in your exponential. And they are the same. So therefore, we can say, okay, the answer there is 8 minus x. What about this? Here again, it's composing inverse functions. So there's two different looks when you compose inverse functions involving a log and an exponential. And again, we've done composing inverse functions with other functions as well. These seem to be the granddaddy of them all, though, the exponentials and logs. So here's the other look. When you have a base being raised to a logarithm, that's your tip-off, and it's the same base, 4 and 4. So that's your tip-off. Oh, to solve this, it's just going to be that log property. When you compose inverse functions, this always is true when you compose inverse functions. The initial input, which is going to be the argument here, equals the final output. So 8 minus x is the answer there. Here, let's just simplify this. How can we simplify that? What does that equal? Sum of two logs can be written as a single log. And since we're adding the logs, we multiply the arguments. So that's going to be the log of male chromosome. XY. Notice the bases are the same. They got to be the same and the same base there. And then what is that base? 10. If you don't see it, it's assumed to be 10. So that's a good log property. We know that. Okay, this one here. Okay, it's another log property. When you subtract logs with the same base, you can write it as a single log where you divide the arguments. Since we're subtracting the logs, the first one over the second argument. So x over y. So that one's done. This one, log base 2 of 1/4. What does that equal? Logs are equal to the exponent. So, or you can think of it this way. Logs are the power. You raise the base to get the argument. So 2 to the what power equals 1/4. That's what we're after here. Doesn't that look like it's going to be negative 2? But if you don't see it, let's continue here. How about 2 equals 1 over 2 squared? Isn't 1 over 2 squared the same thing as 1/4? And then, isn't that... I like to see the base in the numerator. It doesn't do much good in the denominator. So isn't this the same thing as 2 to the negative 2? Oops, I forgot the question mark here. We want to figure out what is this exponent going to be? What is this exponent or power going to be? The answer, in other words. And now we're in that special place now. The bases are the same, they're equal to each other, so the exponents have to be the same. So this is a question mark equals -2. So isn't the question mark going to be -2? So that's the answer, -2. That's the answer there. What about this problem? Another property of logs, if the argument is 1, the answer is 0. I don't have to think about it. What's the equivalent exponential form? We should get a true statement. 8 to the 0 equals 1. The base is 8, so that's going to be my base in exponential form. Logs are equal to the exponent. We got 0 as the answer. That's where the exponent goes in exponential form, equals whatever's left, the argument. And isn't 8 to the 0 equal to 1? Yes. What about this one? This equals 1. Another property of logs, if the base equals the argument, the answer is going to be 1. And sure enough, the equivalent exponential form is true. It doesn't 8 to the 1 power equal 8? Yeah. And then these two are the tricky ones. Not in the real number system. You can't have an argument of a log which is 0 or negative. So, not in the real number system is the answer there. What about this one? Oh, you can tell by inspection the answer is 4. Doesn't 2 to the 4th equal 16? What about here? Well, let's see. Let's answer this one. How about 3 to the x equals 27, I know, is a power of 3. So isn't that the same thing as 1 over 3 cubed? Again, that base is in the denominator. It's more powerful when it's in the numerator. So let's make this our next step. 3 to the x equals 3 to the -3. We got to feel adept at how these negative exponents work. Isn't 3 to the -3 the same thing as 1 over 3 cubed? Sure. And now we're in that special place. It's compact like a Volkswagen. The bases are the same. They're equal to each other. So the exponents have to be the same. So x equals -3 is the answer then. And sure enough, doesn't 3 to the -3 equal 1 over 27? Yep. What is this one? E to the x equals 1. Isn't x going to be 0? Because what's e to the 0? What's any number except for 0 raised to the 0 power? 1? Yeah, I could have gotten fancy and gotten this for my first step. E to the x equals, let's call 1. What's another name for 1, but with that base? How about e to the 0? And then aren't we in that special place? The bases are the same. They're equal to each other. It's compact like a Volkswagen. So therefore the exponents have to be the same. X equals 0. Just as we said, x equals 0 is the answer there. I'll write it over here. X equals 0. That's the answer for that one. What about this? E to the x equals e. Well, we got to know that there's an implied exponent of 1 there. And now, aren't we in that special place? The bases are the same. They're equal to each other. It's compact like a Volkswagen, so therefore set the exponents equal to each other. So they have to be equal. X equals 1. That's the answer. And that makes sense. E to the 1 equals e to the 1. So x equals 1 is the answer for that one. What about this? Ooh, this one looks interesting. It's an exponential equation because I see the variable in the exponent. And what's the best way to solve an exponential equation? This one's tough because 6 is not a power of e. So we got to use logs. Remember, logs unlock the exponent. You know, in general, when you have an exponential equation, try this idea first. Can you write the bigger number as a power of the smaller number? If you can, solve it that way. You don't even need logs that way. But if you can't do it that way, then you're going to need logs. So think of that idea. How do you solve an exponential equation? If you can't do it this way, then think logs. So let's use logs. Boy, this is tough to do with one hand here. Well, let's see. I'm going to do this problem down here. So let's take the ln of both sides. It's a property of logs. It comes up a lot. It's this idea. If you have a equal to b, then this is going to be true. Log base a of a equals log base a. Oops, I'm running out of room here. Log base a of b. So you can do that. You can change each side of this equation or equal sign into an argument of a log, as long as the bases are the same. And that will be a true statement. If this is true, then this is going to be true. So let's use that idea here. So I'm going to use the base e. So I'll write log base e or ln. You know, I'll do log base e instead of ln. Same thing. So take the log of both sides. It's this property right here. And then my argument is e to the x equals log base e of 6. It really helps to solve an exponential equation by that idea of taking the log of both sides. Now, what is this left-hand side going to become? Isn't this composing inverse functions? We have a log whose argument is exponential. The bases are the same, e and e. So when you compose inverse functions, the initial input, which is the exponent, equals the final output. So that just becomes x equals, and then we can just write that as L log base e of 6. And that's the answer. Just like that. Or I could write it as x equals ln of 6. Same thing, right? And then this one here. Well, I already did this over here. So notice I want to solve for x. That 4, I want to get rid of it. Let's first divide both sides by 4. I want to make my variable term bare bones. So divide both sides by 4. Very important to do that. So you got to be in your toes. So that gives us this, because what's 32 divided by 4? 8. And now, just like we did in the last example, let's take the ln of both sides. So from here, we got this. And then isn't this composing inverse functions? And so the initial input is just x here, so that's going to be the final output equals ln of 8. So that problem's done. And let's try this problem here. We're given a sum of 2 logs, and it's equaling to 3. We want to solve for x. We've got x there and x there. So how are we going to solve this log equation? It's good to identify what you're looking at. This is a log equation. I see an equal sign for equation. I see the word log for log. So you know, what you want to do is make it compact. Good things happen when you make it compact. So try to remember that. When you want to solve a log equation, you want to make it compact and then do your properties. So how do we make this compact? We know how to make this compact. When you're adding 2 logs, you can write it as a single log where you multiply the arguments. So that's what I did. I wrote the word log once with the same base 2. And then what's x times x plus 2? Use a distributive property, you get x squared plus 2x equals 3. Now it's compact like a Volkswagen. How do you solve a log equation? You bebop or go to its equivalent exponential form. I love that word bebop. It's like from a Cyndi Lauper song. Okay, so what's the equivalent exponential form of that? Because that looks hard to solve for x here. So convert it to its equivalent exponential form. The base is going to be 2. Logs are equal to the exponent. That's where 3 goes. And then equals whatever's left. The argument. And then what's 2 cubed? Isn't that 8? I kind of skipped a step here. So I have 8 equals this. And isn't this I'm going to include that step. Let me write that over here. 8 equals x squared plus 2x. Okay, so now I included that step. 2 cubed is 8. That's an 8 there. And then you got to identify what you're looking at. This is a quadratic equation. What do you want to do with quadratic equations? Set it equal to 0. So isn't that interesting? We went from a log equation, and then when we bebop to its equivalent exponential form, notice the word log goes away, and now, instead of a log equation, we have we have a quadratic equation, and we know how to solve quadratic equations. You want them to set them equal to 0, so subtract 8 from both sides. So now you have 0 equals x plus 2x minus 8, and then go ahead and factor that, and you get that. And then by the zero factor property, you set each factor equal to 0, you get these 2 answers. But you always have to be in your toes with log equations. They got to be in the domain, whatever you get for x. We get x equals -4, but can we let x be -4 there? No, you cannot have a negative argument. So reject that one. Put an x through it. But this one's okay, x equals 2. You still get a positive argument here as well as here. 2 plus 2 is 4. So that's the answer there. Okay, let's move on to some others. We want to solve this. To solve for x here, we use this property. I already showed you this property. So you gotta, you gotta go through that Rolodex of log properties. And when you see a log on both sides of the equal sign, yeah, you want to think of this property. And it's compact like a Volkswagen. So let's jump right into that property. So we have x plus 2 equals 8. Boy, doesn't that look so much easier to solve than this one? So these log properties are powerful. We turned this lion into a lamb. And if you don't believe me, just listen. Bah! Now this is a linear equation. Let's solve for x here. Subtract 2 from both sides. You get x equals 6. And that is in the domain. So that is good. That's our final answer there. Let's try this problem. Again, I see logs on both sides of the equal sign. So again, I'm thinking of the same property right here. But before we jump into that property, you got to make it compact first. So when you have a coefficient like this, make it as an exponent on the argument, because that's another property of logs. It's this property right here. Let me see, log base a of x to the r equals r times log base a of x. That property comes up a lot, very powerful, as all these log properties are. And these properties go both ways. So here, actually we have the coefficient. So we're going from here to here with this problem. So I'm making that coefficient as an exponent on the argument. So these are equivalent. So that's what I did. I made that coefficient as an exponent on the argument, and I did the same thing here. Coefficient, make it an exponent on the argument. Now, this is more compact than this. Again, when you have an exponent on the argument, it's more compact than when it's a coefficient. And now we can jump on that property, set the arguments equal to each other. So we have this. I want to solve for x, not x to the 1/2 power. By the way, isn't it the same thing as the square root of x? Sir. So what I'm going to do is square both sides. Why do I want to square both sides? Because isn't this a power to a power? And you multiply the exponents. What's 1/2 times 2? 1, which is what I wanted. All right, I want to solve for x, or x to the 1 power. And again, when you have an equation, you can do whatever you want to both sides. So I've raised both sides to the second power here. And then I get my answer, x equals 16, which is in the domain. So that one's done. How about this problem here? Okay, it looks tough. It looks intimidating. But think of that Tom Petty song, I won't back down. Let's make it compact. We're adding 2 logs. Let's write it as a single log. And by the way, there's a coefficient here, so let's take that 3 and put it over here. And then that's the first step. I kind of skipped that step here. So make that 3 as an exponent on the argument. And then when you add up the 2 logs, write it as a single log and multiply the exponents. Oh, this is interesting. I did a shortcut here. If you're on your toes, log base 2 of 4. Logs are the power you raise the base to get the argument. Isn't this a nice integer here? Isn't that the same thing as 2? So, okay, so you could have done it the long way. You could combine the logs and write it as a single log and multiply the arguments, and you'll get the same answer. But this way is quicker. So again, my first step was I made that 3 as an exponent on the argument, and then I made that 2 equals 5. So these are equivalent equations. Let's continue. I want to solve for x. Let's isolate the x term. Let's subtract 2 from both sides. So now we're here. And we want to solve for x here. You got to identify what you're looking at. This is a log equation. What's the best way to solve a log equation? To bebop to its equivalent exponential form. You got to remember that. On a test, if you don't remember that, how are you going to solve for x here? I'll say it again since it's so important. It comes up all the time. How do you solve a compact log equation? Bebop to its equivalent exponential form. What's the equivalent exponential form? The base is 2. Logs are equal to the exponent. Isn't that where the exponent goes in exponential form? Equals whatever's left, the argument. Okay, next. I see this x being raised to the 3rd power. I want it to the 1st power. So let's take the cube root of both sides. So that's what I did here. I showed all my steps. So here's the cube root of the left-hand side equals the cube root of the right-hand side. You know, when you have an equation, you can do whatever you want to both sides. Same thing to both sides. Okay, and then remember that property of radicals? If the index equals the exponent, the answer is just going to be the radicand. So that's 2 equals, and same thing here. The index or root is the same as the exponent. So the answer is just going to be the radicand. It's this property right here for radicals. if your radicand is, say, a, say the root is the generic n, and it's being raised to the n power, here's the property of radicals. That just equals a. Kind of cool. If the exponent is the same as that index. Here I have them both as n. Okay, anyway. And now it's just a linear equation. Add 1 to both sides and we get our answer. And notice 3, x equals 3. It's in the domain. 3 minus 1 is 2. You get a positive argument, so we could accept that answer. You can circle it if you want to. Okay, and then finally, last problem. What is this going to be? 10 is not a power of 2. It's a multiple of 2, but not a power of 2. Like 2 cubed is 8. 2 to the 4th is 16. So I can't do it the nice, quick way where, I get the same, like I did in earlier. So we got to use logs for this one. Logs unlock the exponent. So let's use that property of logs. One of the properties of logs, if you have a equals b, you could take the log of both sides and turn these into the argument of the log. So I took the ln of both sides. Notice I can't use that one property because the base of this ln is base e. And is that e the same thing as that base there of 2? No. So the answer is not going to be x. But I can use that other property, which comes very useful here. Let's bring that exponent on the argument of the log out front as a coefficient. So this is the same thing as that. Okay, and that helps a lot because now it's just a very simple equation here. Divide both sides by ln of 2. And we get that as our final answer. All right. That's that. And have a good night, everybody.